one of the carbons at the allylic positions, adding a bromine, and the hydrogen that was here ends up on the succinamide molecule. That's the hydrogen that's transferred from here. I should draw that one in blue to indicate that's where it comes from. Okay? So that's a result. You can't argue with that one. And what I'm going to try to do is explain it and again show you that the allylic carbons and allylic hydrogens have special reactivity. And if you once one understands this, then you can understand all kinds of even biological process, such as butter going rancid. You guys, even though you're young and vibrant, eventually you'll age like me, and your skin gets kind of bad, and your cells kind of start to get old and weak because this process involving radical cations is part of a biological reaction called autooxidation, where the lipid bilayer in your cells is kind of changed, and it's not as fluid as it is when you're young. So this is conceptually and in reality, it's an important reaction to understand free radical reactions. And this seems to work, I think, in my opinion at least, how to explain what a free radical reaction is, how autooxidation occurs of lipids and other biologically important compounds, and also how polymerization reactions occur. So what's going on here? This is the catalyst. And those of you who occasionally have been listening, whenever I put a catalyst, it's the one you use first. You start off with the catalyst. So what's going on? And in your lab, they probably in the introduction to the lab, they tell you that I don't know if that's a support or argument. That this is a weak bond. And I can confidently tell you that I know that this is a weak bond. And I'd like you to be able to recognize that why this is a weak bond and what other bonds are similarly weak. And what it means, a weak bond means that it's thermally easily broken apart. 80 degrees is not a high temperature. To break a CH bond, you need about a carbon-carbon bond, you need at least 300, 400, 500 degrees. This one is 80, and there's some of them even less. So this, when you heat this, it breaks apart into two alkoxy or alkoxy. That's an O there. Radicals. So why is this a weak bond? And the way to recognize weak bonds is that weak bonds have atoms which are joined by one bond, and they have lone pairs on each atom. Lone pairs don't like each other. Bonding pairs are quite happy to be adjacent to each other, but lone pairs, they basically push each other apart. So that weakens that bond, and it breaks easily. And the way you break it is not into plus and minus, but you break that bond by fish hooks. One electron goes one direction and the other electron goes the other direction. So it's a homolytic cleavage. The terminology for that is homolytic. rather than the usual one we do where the bond is polarized and we give one atom both electrons and we take them away from the other one. So that's the kind of reaction. So other easily recognized weak bonds basically we're looking for that kind of a feature. A fluorine bond. Lots of lone pairs here. Fluorine makes lots of really strong bonds to carbon, to nitrogen, to carbon, to hydrogen, to silicon. But in that case, it makes really strong bonds, but to itself it makes a weak bond. Less than 50 kilocalories per mole, or less than 200 kilojoules per mole, compared to almost 100, less than half the strength of a carbon-carbon bond. The same thing, chlorine. Chlorine is a weak bond. Bromine is really a very weak bond as well. And iodine. So all of those are weak bonds. Also weak bonds are the hypochlorite, oxygen bonded to chlorine. Really a weak bond. You just have to heat those compounds and they will form radicals, chlorine radicals and oxygen radicals. So that's a weak bond because a nitrogen to bromine bond. And you notice that we have a nitrogen to bromine bond in the succinimide molecule. That's a weak bond because nitrogen has lone pair and bromine has. So you can make a list and someone says to me, is this bond a relatively weak bond or is it a relatively strong bond? At least amongst the atoms that we're dealing with in terms of organic chemistry in this course, you should be able to make a case for weak bonds. So that's kind of an aside here, but it's a useful one to recognize, not just from and the weak bonds, they break apart, they form radicals with species with unpaired electrons. And the first property of the most important reactivity of radicals, they would like to pair up their unpaired electron. They're not very happy to having this one unpaired electron. So, and they'd like to make a bond. So, in that system up there, we have generated an oxygen with one electron. So it looks to gain an electron from somewhere else. And all it has in that system, we have two possible sources of atoms that can be transferred. I'm going to put a little extra in via an atom transfer. So we have that. It's a possibility that we could imagine that I just identified for you that the carbon-bromine is weak, bond is weak. You could imagine maybe that what will happen is that